Today we're going to look at the last section of Chapter 1, which is 1.5, Postulates and Theorems relating to points, lines, and planes. Now, most of the things we talk about today should be familiar. We have talked about them to a certain extent, but we're going to be talking about some things that we already know and stating them as postulates and as theorems, and then just looking at some different examples of some situations you guys might see. So, a definition that we need to mention that it's not really mentioned in your book, and so I forgot to mention it by name last time, but it's a linear pair. Linear pair. Think about what that would sound like. Linear meaning line, pair meaning two. So our formal definition is if two angles form a linear pair, then the angles are two adjacent angles whose exterior points are opposite rays. But when you read this word, kind of a quick visual that should pop in your head is a pair of angles, so two angles, that will form a straight line, right? Linear pair. And what this would look like, since according to our definition, we're going to have adjacent angles whose exterior sides are opposite rays. So let's start by drawing ourselves some opposite rays. So to do that, we need our line with our 3 points. I'll call these points A, B, and C. And these form our opposite rays, ray BC and ray BA. And now to create two adjacent angles, we're going to create another point that does not lie on our line. I'll call that point D. And then we're going to connect that with a ray. Now we have two angles, angle ABD and angle DBC, and those would be a linear pair. So we can say here angle ABD and angle DBC form a linear pair. And something else that's important to mention, and this was sort of mentioned in one of the postulates yesterday, one of the versions of the angle addition postulate. Since you have opposite rays along the bottom, right, with ray BC and ray BA, this is actually a straight angle down here. Angle ABC is a straight angle, which means it has a measure of 180 degrees, which means if you apply your angle addition postulate here, you're going to get a sum of 180. So it's also important to realize that linear pairs are supplementary, which isn't a word we've covered yet this year, but you should still be familiar with it. And angles that are supplementary will have a sum of 180 degrees. So again, just a little thing to mention here, that the measure of angle ABD plus the measure of angle DBC is going to have to equal 180 degrees because of our straight angle down at the bottom. And then our final definition is theorem. Theorems are important statements that are proved. So we learned postulates last time. Postulates are just accepted without proof, but a theorem can be explained and must be explained, and we will actually prove some theorems when we get into chapter 2, and that's what will start us off with proofs. So a few postulates to talk about. Now, if you're following along in your book, these postulates are listed on page 23 of your textbook. However, you'll notice they're all named like postulate 5, postulate 6. Those are silly titles that we're not going to be using. Postulate 5 depends what textbook you're looking at, right? Postulate 5 in our textbook could be completely different in someone else's textbook. So we're not going to memorize their titles when they don't have a nice formal title. We just need to understand what is being stated. Now, when we learn our proofs, we will have some postulates and theorems that have nice logical titles to them. And in those situations, we will talk about them according to their title. But like postulate 5 is super generic, and we're not going to call anything postulate 5. So our first postulate is a line contains at least 2 points. A plane contains at least 3 non-collinear points, and space contains at least 4 points, not all in one plane. So we've talked about this. This is just a restatement of things we should already know. A line contains at least 2 points. And these are important things to have in your brain for when we do our always, sometimes, never problems. So a line contains at least 2 points. That means if you have a line, there are at least 2 points on it. So at minimum, let's say we have A and B. But is that all that's on the line? No, that's at least 2. There's an infinite number. And maybe there's 2 labeled, maybe there's 10 labeled, right? But there are an infinite number of points that will actually lie on the plane. They're just not always marked for us. A plane contains at least 3 non-collinear points. So if you have a plane, okay, we can call it, I don't know, plane M. Now, if you have plane M, this is great. I see plane M, but a plane always contains at least 3 non-collinear points. So we're also going to draw points A, B, and C in here. And this is a situation where at minimum there's 3, but there could be a lot more. This is also good to think about for when you have to draw diagrams. If you're going to draw a line, I need to see 2 points on the line. Because if you have a line, you automatically have at least 2 points. If you draw a plane, I need to see 3 non-collinear points in that plane. Because again, to have a plane, you must have at least 3 non-collinear points. These things will always go hand in hand in our drawings. The second one says through any 2 points, there is exactly 1 line. So very similar to our first statement, just kind of reversed. So if you have 2 points, I'll call them C and D. Through those 2 points, there is exactly 1 line. Through any 3 non-collinear points, there is at least 1 plane. So again, you have 3 non-collinear points. I'll call these E, F, and G. If you have those points, you have at least 1 plane that is a terrible plane. But if you have those points, there is at least 1 plane that is formed by them. Okay, so very similar to our first statement, or just our phrasing is a little reversed. If 2 points are in a plane, so let's think about what this looks like. We're just going to take it bit by bit. If 2 points are in a plane, so that means you have a plane and there are 2 points in it. I'll call this A and B. Then the line that contains the points is in that plane. Okay, so you have a plane, there are 2 points in it. Well, are there only 2 points? No. If there's a plane, there must be at least 3 non-collinear points, so I got to put in that 3rd point. And then the line that contains the points is in that plane. So again, if 2 points are on the plane, then the line that contains the points is in that plane. So let's say I have my 2 points A, B. Through any 2 points, there is a line. So if basically what this is stating is if points A and B are on your plane, then the line that contains them is also in the plane. And you could also connect B and C with a line. You could connect A and C with a line. Right, there are several lines that could be drawn here. And then last postulate, if 2 planes intersect, their intersection is a line. There are several ways you can draw this. You can see some examples in your textbook. If you struggle with these drawings, a quick and easy way I like to draw 2 planes intersecting, visualize like a book, right? If you open a book, the covers of your book are planes. So what I do is I draw kind of like a vertically positioned plane like this. Don't forget your 3 points on it. I'm going to call my non-collinear points X, Y, and Z. And then I'm going to draw another plane kind of coming off of it to the right here. And I'm going to call those points A, B, and C. So right now I have plane X, Y, Z intersecting plane A, B, C. And then it says here, if they intersect, their intersection is a line. So I would also have a line at the intersection, and that might have some different points in it. Or maybe instead of putting all those points kind of scattered about inside, maybe instead I had put like point A here and point Y here, something like that. Okay, so then my two planes would intersect at line YA. There's a few different ways you could draw that. That's just one example if you're struggling with drawing two planes intersecting. Through a line and a point not in the line, there is exactly one plane. So this is saying you're going to have a line. I'll call these points whatever letters you want to pick. Completely up to you. How about A and B? So through a line and a point not in the line, so we're going to draw something non-collinear with it like C, there is exactly one plane. And the reason that occurs is your line is going to have 2 points, and then there's going to be another point that is non-collinear with them to form your plane. If 2 lines intersect, then exactly one plane contains the lines. So let's draw our 2 lines intersecting. Draw this however you like, but I'm going to draw my 2 lines intersecting. I know my 2 lines have to have at minimum 2 points on them, and then in addition, I'll label the intersection separately. If I have a situation like this, exactly one plane is going to contain all these lines because the points on the lines are all non-collinear, right? You could pick a variety of these different points to make a line. Visualize like if this was a nice big vertical plane, right? All these points could line up nice and vertically, and you could draw a vertical plane through them. You could, maybe these are lying flat, right? You could draw a horizontal plane through them. But these points here are non-collinear, right? They would be coplanar, so they're all going to be contained in the same plane. You just have to visualize that in a few different ways. And then in the next video, we'll look at some examples.